Welcome to this technical packet flow. Today we examine the packet flow inside the Cisco Secure Firewall. We often call this FTD or Firepower Threat Defense. But first, we must understand the core architecture. FTD is a unified software image. It combines two distinct processing images. The first one is LINA Engine, which stands for Linux Network Architecture, and the second engine that it uses is Snort Engine. LINA Engine comes from Cisco traditional firewall, that is ASA, which handles layer 2 through layer 4 routing, switching, and stateful inspection. Snort Engine basically handles the deep packet inspection. For example, intrusion prevention system, the layer 7 application visibility control, the malware filtering, the file filtering, and whatnot. The yellow boxes that we are seeing here, LINA Engine part, and the green box are entirely the Snort Engine part. But to communicate between these LINA Engine and the Snort Engine, to make this possible, there's come the DAQ. DAQ stands for Data Acquisition Library. DAQ acts as a translation bridge. It moves packets between LINA data plane to Snort data plane. Let us trace a packet from ingress interface, and we'll cover this in a moment. So when the packet gets received on the ingress interface basically takes some parameters whether to accept that packet or not. There's a rent frame, jumbo giant frame, input queue, output queue. Rent frame basically means any packet size less than 64 bytes, and jumbo giant frame is basically the packet size in between greater than 1500 bytes and up to, which goes up to 9000 bytes, is called jumbo frames. To understand about input queue and the output queue, every interface have a buffer memory. Every device has the buffer memory in the interface, and each of them known as input queue and output queue. Understand this by when an inbound connection or inbound traffic is going to hit on the interface, then that inbound traffic is stored in that input queue buffer. That is called the input queue. And when the traffic is going for the outbound traffic, then that outbound traffic is stored and it is called as output queue. These are some parameters that ingress interface is going to check. And then if everything is fine, then the packet moves from ingress interface to the next step. But while moving to the next step, here comes the defrag policy. What happens at defrag policy, or what it is? When the large packets are fragmented to match the empty queue, that is 1500 bytes, thus only the first packets. If I have multiple fragmented packets, then only the first packet is having the UDP or the TCP port number, which is actually firewall needs to check the port number, check its existing connection table, whether their connection is existing in that connection table or not. In a firewall, connection table basically relies on the five tuples. Five tuples on what are those five tuples? That is source IP, destination IP, source port, destination port, and the protocol. Because of these five tuples, connection table is going to be made. And if the connection table have these information for that traffic, then it is going to use the fast path lane. If the connection table don't have that traffic detail stored in their connection table, then it is going to unnat or the next step. That is why defrag policy comes into play. And then it handles to the existing connection table. If existing connection, then go to this fast path, and this fast path is actually land our packet directly to the Snort DAQ module. But in this case, we are assuming we don't have any existing connection in the connection table, then we are going to look into the next system, that is unnat or egress interface. Before that, I want to tell that if there is any VPN connection or tunnel traffic is there, then VPN decryption is going to take place before unnatting or egress interface, that is NAT divert. Now, when the packet receives on this module, unnat or egress interface is going to happen. What both of them? Let's understand this one by one. Understand in this way that basically FTD works on the zero trust architecture. So whatever the interface is, whether it is inside zone or outside zone, it doesn't matter. For FTD, it's totally untrusted world. And that happens whenever data traffic come from mapped world towards real world. Then untranslation basically happens. And that untranslation is nothing but the unnat thing. Egress interface, a special type of conditional NAT which uses a special keyword with NAT, that is divert, which means NAT divert is going to forcing the traffic directly to bypass everything and reach to the L3 route, that is route lookup. So this is the egress interface, and we are just assuming that we have a NAT policy there. So a NAT is going to happen, and our packet is now going to reach pre-filter policy. What is pre-filter policy and what it is? Pre-filter policy provides an early access control, that is EAC. EAC is a feature which gives the liberty to the firewall that bypass the Snort engine, and it can bypass the Snort engine and can reach to the flow update module. How it comes into play? Whenever you have configured the early access control with fastpath, then run show access list. And with this command, we can see the EAC rules, early access control rules, is always at the top of the rules, ACL policies, because ACL runs from top to down behavior. So the very first rule is going to match. And because of that fast path, our packet is going to skip or bypass the Snort engine and reach to the flow update module. But in this case, uh, by default, analyze is there. And in this case, we are also assuming that we are going to analyze the traffic. Block means basically drop the packet. So now our packet is going to analyze and send towards the L3, L4 ACL. L3, L4 ACL having options to choose or to configure from. Allow basically gives the LINA engine the permit command, and in Snort is going to give the verdict to the LINA engine. In trust LINA, it's also known as trust only, and in Snort is not going to any verdict. No verdict is given by Snort in this case. If the traffic is marked as trust. For monitor, LINA engine says permit the traffic. But on the Snort part, the Snort engine, it says just audit the traffic. Auditing is only the key role, which means it creates the log for that, and logs is only going to be created. Snort is not going to permit or deny any type of traffic only. Only Snort is going to have the events saved in the logs format and nothing else. That is called auditing. Next comes the block. Block basically in LINA for LINA also deny, and for Snort is as well it is deny. Block with reset is similar to like block, but with reset, which means it actually blocks and sends the TCP reset packet to the sender. Interactive block going to prompt a message to the sender that was request that you had made is blocked by the administrator. Interactive block with reset also similar works is this, but it sends the TCP reset message to the sender. To view the access list in the LINA engine, we have the basic command that is to access list. And to see the not how Snort is behaving for those LINA access lists, and go to the expert mode in the CD and then run this command. Now our packet is ready to send to the DAQ part. DAQ, that is data acquisition library. DAQ communicates with ASA data path and processes it through PDTS, that is packet data transport system. DAQ take the packet and store it in a memory. For example, memory address is 0x0101. DAQ not going to transmit the entire packet to the Snort engine. Instead of that, it actually shares the memory address that is 0x0101. This memory address is shared to the Snort engine, which also saves memory. By sharing memory references instead of passing the entire packet, it significantly reduces CPU overhead and memory bandwidth. Before moving further ahead, I want to tell Snort verdict is handled by the LINA only. Snort process doesn't drop anything in between. Like we can see here, many modules saying drop, but it doesn't going to drop the traffic. It's only going to mark it. LINA engine is the only responsible whether to drop or not. Our packet comes to the L2 L4 decode part. See, LINA and Snort are entirely separate software processes running in their own memory spaces. When DAQ passes the packet as it is from the LINA to Snort, Snort does not inherit LINA's understanding of that packet. DAQ just hands Snort a raw buffer of bytes, for example, ones and zeros. So before Snort can run any DPI processes, it runs them through packet decoder or L2 L4 decoder. which is the foundational preprocessor in the Snort engine. And that's what L2 L4 decode is. Then our packet moves from L2 L4 decode to security intelligence, which check for the IP addresses. Security intelligence IP addresses works on two things: blacklist or the whitelist. If the IPs are on the whitelist, it has the higher precedence over the blacklist and it will allow the traffic. For blacklist part, there are two options: manual or auto. For manual process of blacklisting an IP address, administrator can explicitly select an IP and make them block. That is manual. To make the blacklisting possible automatically, there's a tool called Talos that makes that happen. Talos Cisco intelligence database and checks each and every IP that is compromised or being shared in the internet that is malicious or harmful for the user. To check whether that IP address is blacklisted or not, just go into the expert mode and then run this command. Suppose our IP is clean and pass this check, then our packet moves towards the SSL group. Here we again see the defrag policy. Let's understand why this defrag policy comes. The earlier defrag policy that we have seen here, this defrag policy works on layer 3, which reassembles multiple fragments it to existing connection table to understand these parameters. But here, this defrag policy in the Snort engine happens at layer 7, which means the TLS records gets assembled here at application layer and then handle it to the SSL decrypt. Now, SSL decrypt have some options to configure from. There are multiple options as decrypt resign, decrypt known key, do not decrypt, block, block with reset monitor. Let's understand there is decrypt resign and decrypt known key. Let's first understand what is decrypt resign is. There's a TLS tunnel. A TLS encryption is going to happen first between the client and the firewall only, and then another TLS is built between FTD firewall to the server. When the client wants to request something, it reaches to the FTD. FTD uses its own key materials to generate the key and to decrypt that packet. And again, if everything is fine, it again encrypt it and send it towards the server. In response, server will reply and it will again decrypt it. FTD knows keys, so FTD again decrypt this, and after decryption, if everything is fine, then it sends to client. This is what resign is. It is basically man in the middle thing, where it intercepts the packet, again encrypt it, and then send it to the server. Again, in the same process, vice versa. To understand the decrypt known key, we all know that to make the TLS connection possible, everyone have its own public key with associated with its private key. The same public key is shared. Now, FTD also knows the public key. The TLS that is made between the client and the server is also being shared with FTD as this key. The FTD also know the key to decrypt it. So when the FTD receives it from the outside zone, it decrypts it because it has the key. And again, after running the Snort processes, then only if it passes, then it encrypts it again using the same key and then send it to the inside zone. In this case, client and FTD both have the same key that uses to encrypt and decrypt the packet over the TLS. That is what decrypt known key is. By default, do not decrypt is there set for the SSL decrypt. Block means block it, block with reset, that is TCP resets message to the sender and monitor is there. Now my packet is sent to the security intelligence to the DNS URL. Security intelligence uses the Talos that I mentioned earlier. That is the intelligence source of Cisco where the blacklisted IP address or the malicious DNS, malicious URLs is there. For example, malicious URL can be also as a C2 act as a C2 server, where C2 server that is command and control server that uses to control the botnets. If a server is malicious or flagged for the any malicious activities, that is not going to open. The administrator can configure the DNS on these options: whitelist, monitor them, domain not found, drop that, or sinkhole. After that, the packet sent towards the identity policy. In identity policy, we uses the user's identity profile. In modern security architecture, because of DSCP, NAT, or mobile devices, IP addresses can't tell which user sent that request. So identity policy's sole job is to map IP address to the user group. It actually works on two methods, whether the passive authentication or the active authentication. Passive authentication, where a NAC solution, that is network access control solution, for example, the Cisco ICE, authenticates the users and learns its IP addresses via 802.1x or via AD logging. Then it publishes using the PixGrid protocol to the FTD. But in the absence of the passive authentication, then active authentication comes into play, where it will intercept the user's web traffic and can redirect them to a web portal asking for username or password before allow traffic to continue. Now, the packet sends towards the L7 ACL, where the AVC comes into play, that is application visibility control. For example, we have a website that is Facebook. We have many features in Facebook, for example, games, chats, comments, likes, and many more. But using AVC, we can block such things. I want to allow Facebook posts to get like and comments, but I want to block chats and games. Games and chats is going to block. Using AVC, we can do that. When our packet is going to send to the QoS classifier, we are just marking the data or the packet. It actually gets enforced down here in the LINA process. QoS actually acts as a rate limiter policing on the interface, like it enforces the policing independently in the both direction, whether in the upload or the download. For example, I had rate limited 1 GB data only for the upload part. Then when it exceeds, it's going to block it. I have limited 10 GB of data for download direction. Then after exhausting the 10 GB of data, then it's going to stop it. That is what QoS classifier means. Now the packet when sent to the network discovery. Network discovery, two types again, that is active and passive. By default, passive is set, which means builds its network map by silently monitoring active, passive, whatever the traffic is, without injecting any extra packets against it. Like it extracts information, for example, application details, operating system fingerprints, where it gathers it from HTTP user agents, and also we can make network discovery as active too using a tool called we all know about it, that is nmap or network mapper. We can actually use nmap to schedule it to run automatically, or we can also use it manually. We can make network discovery as active too. It sends specific packets and evaluates the response to accurately identify exact operating system and its version of open ports or running services. Now the packet sends to the file policy. Here we have two options. First, whether the file is sent towards the AMP cloud, where the file hash, not exactly the file, what file policy is going to do, an xyz.pdf file, it runs an hashing algorithm, that is SHA-256, and give this hash value to the AMP cloud via internet. And if that hash has some malicious history, then this AMP cloud will send it the response. If it is a malware, then it's going to store it for an hour. If it is a clean file, then it is going to store the information for 4 hours. For malware thing, there is also one thing that I want to mention, that is Spiro analysis is there is an option. Or if I want to perform a local analysis for the file, whether that file is malicious or not, FTD downloads a database set from ClamAV that is acquired by Cisco only. So the ClamAV has some data signatures of malicious files, and to check for the malicious files, it uses the ClamAV. Now after that, the pack goes to the Snort rule. Snort rule is a advanced version where FTD performs and update its intrusion policies. It's text-based rules for identifying attacks like SQL injection or buffer overflow or even web server vulnerabilities. To have a look on Snort rule, how it looks. Snort rule resides in two parts. That is, first one is rule header and the second one is rule option. In the rule header, we define the action, the protocol, the source, and the destination. The direction plays a key role here. If the direction is from left to right, then the source is this and the destination will be on the right side. If the arrow direction is this, then the first destination comes, then the source is going to play. In the rule option there is a message that needs to be shown to the administrator and with a SID, unique identification of that particular event or the rule. After all this snort processes, the snort rule is last step, and then it is going to send the snort verdict to the LINA, whether to drop, accept, permit or not. Now it goes to the flow update module. Flow update simply updates the internal connection table by updating the byte counters and resetting the idle timer. Now the packet sends to the ALG checker checks, or ALG stands for Application Layer Gateway. Due to some older or complicated protocols, for example VoIP or FTD, which actually write their internal IP address inside the actual message. So with that, internal IPs also need to be changed. So the ALG checks does that. It also changes the internal hidden IP address too. If it is not going to do this, then when this packet receives to the receiver is going to send the packet to the IP that resides inside of that packet. Now the packet is going to the NAT IP header. NAT IP header is going to translate the outside IP header, translate that into it, and then send it to the QS enforce. Earlier, the QS classifier that we discussed, that is rate limiter, is enforced here in the QS enforcement. Then the packet sends to the VPN encrypt, that is a tunnel traffic. Then VPN encryption is going to take place. Then it sends to the route lookup, where it looks for the next hop table. If the route is there, then it sends to the L2 address. L2 address going to put the MAC address labeling or layer 2 addresses. Then it will send it to the outside interface or egress interface. And if it is not there, then it will going to drop it. And that's all from this packet flow. I hope you would like it. Thank you.